Yeah, okay, so I'll start now. Okay, so welcome everyone. We are back after brief hiatus, and this is the first talk of the semester. So as usual, remember you'll have to mute yourselves during the talk, and we will go around the table in a little bit. But the operator for today's talk is Zeev Dvir, and behind the scenes we have Thomas Hollenstein, Thomas Videk, G. Kamat, and Klamakanon. And now Zed will introduce the groups.
Okay, thanks, Anindya. Let's quickly go around the table, see who's with us today. We have a record number joining from Europe. So let's see first Clément Canon with a group from Colombia. Hi, Clément.
Hi.
Hi, guys. Hi, Rocco. Joop Priet, and I see Harry, and they're joining us from CWI in Amsterdam. Hi, guys. Lila Fondes, hello. The group from Paris. Hi, guys. It's always very dark there, but good to see you. Pierre Srivastava from Caltech. Hi, guys. Hi, whiteboard. Oh, hi, Hollander. And Shravas Rao and Hak here from NYU. Hi, guys. And the group with the Simons Institute in Berkeley. Everyone, and the group from Weizmann Institute in Israel. Oh, big group. Hi, everyone, and that's it. So back to you in India.
Thanks for that. So we have some exciting talks lined up. In 2 weeks from now, Harry is going to speak about catalytic computation. And 4 weeks from now, Alan Sly is going to speak about K-SAT threshold. Now, today's talk, our speaker is Zeev Dvir. He is an assistant professor at Princeton, and he has done work in complexity, de-randomization, coding theory, incidence geometry, and the list goes on. He's probably most famous for resolution of the finite field Kakeya conjecture, which was a really big result. And today he is going to speak about another breakthrough result, sub-polynomial communication for two-server private information retrieval, a problem which was open for, I guess, 2 decades. So Zeev, you can start now.
Okay, thank you. This is very exciting, and thanks to the millions of viewers around the globe. It's hard to tell if people are laughing at jokes during the talk, so this makes it very hard for me, but I'll just assume everybody is laughing hysterically, like now. Okay, so this is joint work with my student Shivakant Gopi from Princeton, and so the setup is Private Information Retrieval. It goes back to Shor Kushilevis Gordolf in Sudan. So you have a user and you have a database of n bits that's stored on a server, and the user wants to retrieve one of the elements in the database, but he doesn't want to reveal the identity of that element to the server. So he wants to keep his privacy. And the database entries, they don't have to be bits. This just makes it a bit simpler, so they can be phone numbers, records, any other list of elements. And that's the basic question. And formally, we're asking for a very strong notion of privacy, probably the strongest possible notion of privacy. So we ask that the distribution of the messages sent by the user are completely independent on the identity T. So if you have this very strong notion of privacy, there's basically the only solution that satisfies the strong guarantee is for the server to send the entire database to the user. And then there's, of course, the user has its privacy, but the communication is very high. It's n. For n bits, you have n communication. And the question is if you can lower the communication. And there are two approaches for lowering the communication. One is a cryptographic approach, where you change the definition of privacy. You ask for computational So privacy only against the computational bounded adversary or server. And that's one line of work that I won't talk about at all. And the other line of work in which this work belongs to is when you have more than one server and you keep the definition of security, of privacy the same. So, and we'll see what this means in a second. So, here's the definition. We'll talk about two servers, which is the simplest and, again, the hardest case to implement. So you have two servers. The servers are non-communicating. And both servers share the same database, same end bits. Now, the user can interact with each server, and we want the distribution sent to each individual server to be independent of T. So if you just look at one part of the communication, so the communication with the first server, all the messages sent by the user are distributed independently of T. So, for example, the user can just send uniformly chosen elements in some set. And the same holds for the second server. And somehow the identity of the element is encoded in the correlation between these two distributions. So, so each server can't tell anything about the identity of the element. And we'll focus on one-round protocols, which are the simplest. It captures most existing constructions, where the user sends one message to each server. Each server answers with one answer, and then the user can compute the bit AT. And we'll, again, focus on perfect correctness, which means that the user always recovers the bit. So there's no probability of error. And any questions about the model so far? I'll try to give a few seconds for questions because it seems technically a bit complicated to ask a question. So, all right, no questions. So the cost of the protocol, which is the quantity we're interested in, is the total number of bits sent back and forth between the user and the servers. So to survey some of the known results on this model, so the first paper already gave an n to the 1/3 communication protocol for two servers, and then there are a couple other works that achieve the same cost for two servers, and basically there was no progress since then for two servers. Progress was made for more than two servers. So for K servers, there was first a protocol with n to the 1/k communication, then n to the 1/2k minus 1, then n to the log k over k log k. So again, some exponent depending on the number of servers. And then the really big breakthrough came with the work of Yekanin and then Efremenko. And they showed that with 3 servers, you can already go to sub-polynomial communication. Oh, I can see text questions. That's great. I assume k is not allowed to depend on n. Yes, k, the number of servers k is a constant. Think of it as a small constant. You can also look at, for example, if k is logarithmic in n, then you can already have very long case. In this talk, I'll focus in a minute only on k equals 2. So, but you could also have k depending on n. Actually, it's not a unreasonable thing. Okay. Any other questions? Okay. So the early works up to Yekanin and Efremenko, all the works were basically relying on some kind of a low-degree polynomial interpolation, basically starting from Reed-Miller codes and building on that. And the big difference with these newer results of Yekanin and Efremenko is that they use a different family of error correcting codes called matching vector. So they're based on something called matching vector families, which we'll see in detail. And this really allows for this huge savings in communication. And what we do in this work, we basically reduce the number of servers from 3 to 2 using this matching vector family machinery and adding to it some more technical ideas. So, so we will see the ideas a bit later. And the actual communication is, again, exponential in square root log n, basically. So that was the communication for 3 servers, and now it's for 2. And okay, so go on. So what about lower bounds? What do we know about lower bounds? The best lower bound for general 2-server schemes is by Werner and de Wolf, and it's very low. It's 5 log n. So log n would be the trivial lower bound, and 5 log n takes much more work. And there is a very interesting work of Razborov and Yekanin, which shows that n to the 1/3 is actually tight for all previous constructions. So they define a restricted model called bilinear group-based schemes. And they show that all previous schemes fall into that category. And if you're in this category, you can't beat the n to the 1/3 construction. Now, our protocol is actually bilinear, or it can be made bilinear, but it's not group-based. So the thing with group-based, it's a technical term that takes about a page to define. And so the protocol it uses groups, so it's not completely unrelated to groups, but it doesn't satisfy this long technical definition. It satisfies the slightly weaker definition from the same paper, so it employs a group-based secret sharing scheme. And again, I don't want to go into these definitions, but for those in the audience that know the difference between locally decodable codes and locally correctable codes, this is a similar difference. So our schemes are based on locally decodable codes, and the old schemes are based on locally correctable codes, it's a stronger notion. So the old scheme actually gives you something stronger than you need. And you can decode not just the bits of the database, but also some other functions of the database. So that's why they get stuck at n to the 1/3.
Zeev, I have a question. So these lower bounds, do they hold for multiple rounds of communication or just for a single round?
I think they're for single round, but I'm not 100% sure. I think the Razborov Yekanin I think it's only for 1 round. But all the protocols, I mean, I wonder if 1 round is actually, if you can prove that that's enough without loss of generality. I mean, it's a good question, actually. It's a nice open problem. As far as I know, it wasn't looked at. If 1 round is enough for 2-server peer. And any other questions? Okay. So these are the lower bounds, and so the rest of the talk I want to start by overviewing the existing constructions, and then see how to extend them and reduce the number of servers to reduce the number of servers to 2. And actually, instead of starting with a 3-server scheme, I want to start with a 6-server scheme. It just makes the reduction to 2 servers a bit simpler. It's not a big distinction. So this is a 6-server scheme from Fermenko's paper, which is based on Yekanin's kind of earlier work. And I'm going to actually describe it in a way that's different from the way it's explained in these first 2 papers. And so there's a paper, it's a joint work with Gopalan and Yekanin, in which we interpret these schemes as actually based on polynomials. And this point of view makes it easier to see the improvements that are going to come later. So there are 2 ingredients in the construction. The first one is a matching vector family. So this is a family of vectors in Z6 to the k. So you have 2n vectors, the red ones, the u1 up to un, and the blue ones, v1 to vn, and each one is a list of k numbers modulo 6. And we're picking modulo 6 just because we want to get 6 servers. And also because it's a product of 2 primes, which is important. And a matching vector family has a property that if you look at the inner products, mod 6, between the reds and the blues, then you get 0 mod 6 only if I is equal to j. And you get non-zero mod 6 if I is different than j. So that's a matching vector family. And the amazing result of Grolmusch from 1999 is that these families, there are very large families if you look mod 6. So basically, mod 6, you can construct such families where the number of elements is super polynomial in K. Or in other words, if K is sub-polynomial in N, in the size of the family. So this is impossible if you replace 6 with any prime number. So this is only because 6 is a product of 2 primes. Yeah, so this is the main ingredient, and this is where a lot of the magic kind of happens. And I'll mention later the open problems about the biggest size of such a family, which are if we could answer these questions, we could also maybe reduce the communication to something much lower than just sub-polynomial. So this is one ingredient. The second ingredient is it's a finite field, FQ, that contains an element gamma of order 6. So for example, if you take 3 in the field of size 7, it has order 6. If you take the powers of gamma up to gamma to the 6, you go back to 1. So the group generated by gamma is a cyclic group of size 6. So we're going to use both of these, and somehow we'll use gamma to encode these matching vector families, and the mod 6 action will happen in the exponents of gamma. But the scheme itself will be over the field FQ. So these are the two ingredients. And just to set up some basic notation, so this is going to simplify a lot of the calculations. So if you have two vectors, x and e, then x to the e, I'm using it to denote the monomial, x1 to the e1, x2 to the e2, xk to the ek. So a vector to the power of a vector is a number. It's a field element. And the other notation is if I take gamma, this field element, and I raise it to the power e of a vector, I'm thinking of this as a vector. So it's gamma to the e1, gamma to the e2, gamma to the ek. So this will become clearer later. Okay. So here's the 6-server scheme. We take the database, and we do the following thing. We define a polynomial in k variables. So k is the dimension of the vectors in the matching vector family. So we have a polynomial in k variables, and the polynomial on monomials x to the ui. So you take the red elements of the matching vector family, and each one of them defines a monomial, and x to the ui, and then the coefficients of this monomial is ai. So so the monomials in the polynomial are fixed, and we just pick a subset of them that correspond to the ones in the database. So the database defines this polynomial, and now we take the polynomial and we're going to evaluate it. So the communication is going to involve evaluations of this polynomial, and the evaluations are going to be only over not over all the points in the field, but only over points that are powers of gamma. So we're going to take vectors that such that in each point in the vector is a power of gamma. So this is a subset of FQ to the n to the k that has the same structure as Z6 to the k. So it's identified because gamma is of order 6. Every coordinate can have 5 values, so just powers of gamma, and there's a 1-to-1 correspondence between Z6 to the k and this set. So you can think of each server as just having this big table of values, even though they don't really have to compute the entire table. They can just evaluate the point on the fly when they need to. OK, so here's the protocol. The user picks a random point in Z6 to the K. Let's call this point Z. And then he looks at the line. So this is the line in Z6 to the K in direction VT. So remember, we want to retrieve AT. So we pick the blue vector in the matching vector family whose index is T. And this defines the direction of the line. And so we take a random line in this direction. So and then we look at the restriction of this polynomial PA to this line. And again, we put the line in the exponent. So this is basically gamma to this vector. So we can evaluate. It's kind of an exponential line. It's an additive line in Z6 to the K, but when we identify Z6 to the K with gamma to the K, it's not really a line in the field. It's kind of an exponential line. So now the main point here is, if we look at the restriction of PA to this line, and that's the claim that we need to prove, this happens to be a degree 5 polynomial in a new variable, big S, that's defined as gamma to the S. So if S is the shift on the line, so S can have 6 values, 0, 1, 2, up to 5. And for each value of S, we get a point. And even though it's an exponential line, we still have, we can say something about the restriction to this line. We can say that this restriction, if you do this change of variables, it's a degree 5 polynomial. And that's not hard to see because the order of this element, the order of S is 6. So if I raise S to the power 6, I get S back. So the fact that it's a degree 5 polynomial is not hard, but the interesting part is that the value at 0, or the free coefficient of this polynomial, is exactly what we are after. So let's prove this. Maybe the calculation will make this a bit easier to see, and then let's see if it's clear or not. So here's the polynomial. So remember, the monomials correspond to the red elements in the matching vector family, and now we're taking a restriction to a line whose direction is chosen to be VT. So it's a specific blue vector. Okay, so we just plug this in, and we use our notations, and the main thing to observe is that if you take gamma to the Z plus SVT, so this is a vector. It's gamma to the first element, gamma to the second element, and so on. If you evaluate this monomial that corresponds to UI at this point, you get just gamma to the inner product. And that's so usually I try to use a blackboard to do this calculation, but any questions, by the way? I can see a small picture, so if anybody's unhappy, you can do this with your hand. Okay. Anyway, it's a simple calculation, so that's what you get, and then you can start playing around with it. You can take out the part that doesn't depend on S. So S is the new variable. That's phi of S. That's the restriction. And everything in the exponent happens mod 6 because gamma is of order 6. So now we're going to gather together the different powers of gamma to the S. That's our variable. That's the big S we define, gamma to the S. So we want to have a polynomial. So we want to compute the coefficients of this polynomial. And so let's see, the free coefficient. This is the coefficient of gamma to the S to the 0. So it only comes from inner products between blue and red vectors that are 0. but we know that there's only one. There's only going to come from UT. So we're going to get the coefficient AT, gamma to the Z inner product UT, which we know. So we know Z, I mean the user knows Z. So if the user gets this free coefficient, the user can compute AT. So, and then we have the rest of the powers, and there are some coefficients. CR is the coefficient of gamma to the S to the R, and CR is just going to be the sum over all terms, AI gamma to the Z UI, where UI inner product VT is R. So just group this polynomial restriction groups together things according to their inner product with VT. So because we have this isolating property of the matching vector family, we can isolate one of them to the free coefficient. So that's exactly what we get. We get a polynomial in the new variable big S, such that the value at 0, or the free coefficient, determines the bit. And now the protocol is obvious. So the user is just going to ask each server for the value of this polynomial at one point. So you ask server I for the value of the polynomial at gamma to the Z plus I VT, which is just this restriction phi of I. And the value that you're sending to the server is just a uniform point in Z6 to the K, or this is K. So you're not giving any information to each server, and that's the usual kind of PCP or peer kind of. Each point on a random line is independent, but if I give you 2 points, it reveals the line. But as long as you only have 1 point, it doesn't give you any information. And then the user can interpolate the polynomial from 6 values and compute the coefficient, the free coefficient.
So Zev, just to clarify, this point is not random in FQ to the K.
Right, but it's random in Z6 in gamma to the, yeah.
Okay.
We're only interested in a set of size 6 to the n inside FQ to the n. It's only the powers of gamma. So if you take a field of size 7, then you're basically only looking at evaluation points with no zeros. And then you're taking a random point there. So you're right, it's not a uniform point in FQ to the K, but it's a uniform point in a subset of it. And the subset is fixed. Any questions from Weizmann? Okay, guess not. How's the beer?
Zev, so this
yes.
The set that you're over, I mean, this is essentially what is a group? I mean, this is Z, the multiplication, the group of multiplication, this Z, the non-zero of vectors in F7.
Yeah, it's a group. It's a abelian group under pointwise multiplication.
Good. Okay.
It's isomorphic to Z6 to the K.
Thanks.
All right. So okay, so that's the old scheme, and as you see, it's quite non-trivial. And now we're going to make it even more non-trivial to reduce the number of queries from the number of servers from 6 to 2. And we'll do it by adding partial derivatives. Sorry, was there a question by? Okay, I'm hearing voices.
There is a question. We have a question.
Yes.
Here.
The question was, isn't I is 6 the same as I equals 0? So maybe I'm missing something simple. Because
yeah, it's 6 is like 0. So instead of 1 to 6, I can write here 0 to 5.
Right, but you want to get g of 0, right? So you shouldn't be reading g of 0.
But that's when I'm only evaluating it at powers of gamma. I'm evaluating it at 1 gamma squared, gamma cubed, up to gamma to the 5, and I'm getting back the value at 0.
Okay, fine, got it. Thanks.
Okay, great. So if this is not clear, then there's really no point in going further. So if there are any other questions, that's a good time. All right. So Okay, great. So you see the magic kind of happens in the matching vector family, but there's also, even given the matching vector family, there's still it's still a bit complicated. So we're not going to touch the matching vector family. We're going to just try to group together information, trying to get more information from each server, basically, without sending the server more information.
So maybe just
Yeah.
Just to clarify again, Venka's question. So the polynomial G, you're evaluating it so it's a polynomial on a field F7, right? And you're evaluating it at powers of gamma, so like 1 gamma squared. But we actually want its value at 0, right? We should not the power of gamma. Okay.
Yes. Yeah. It's also the value at 0. Maybe it sounds a bit weird. We're just interested in finding the coefficients of the polynomial. It's not. Right. Okay. And right, so the cost of the polynomial is just sending back and forth points in Z6 to the K. So it's O of K communication, which is, again, it's sub-polynomial because the matching vector family is of super polynomial size. So, okay. So now to get the number of servers down, we're going to do something that it seems very natural, but then it also seems like it shouldn't work. So we're going to try and, instead of obtaining the value of this polynomial restriction at 6 points, we'll try to get the value and the derivative and the second order derivative at 2 points. So we'll try to get the servers to send us more information in a way that will enable us to get not just the value at the point, but also the derivatives up to order 2. And if you have a polynomial and you have 2 points and the derivatives of order 2 in both points, you should be able to recover it because it's a degree 5 polynomial. So you have six values, which should be enough to recover the polynomial. And that's not a new idea. This is inspired or very similar to the 2 server protocols of Woodruff and Yekanin. But again, their protocol is based on Reed-Miller codes. And so they have polynomial communication. But we're going to try and somehow use a similar idea on this new family of codes. And the cost is going to grow, but it's only going to grow in a polynomial way. So it's going to go from K to polynomial in K, but K is sub-polynomial, so it's still going to stay sub-polynomial. So okay, so let's see how it works, and we'll also, the main question here is why, if this works, then why can't you just get the derivatives up to order 6 and reduce it to 1 server? And so that would become clear later. But let's just see why this works for now. And so let's go back for a second and look at this is basically the Woodruff-Yekanin idea. It's how to get the derivative of a restriction to a real line. And by real, I mean, I don't mean the real numbers, I mean just a line, not an exponential line. So a line in a finite field. So let's say you have a polynomial, and let's say you restrict the polynomial to a line. And now, so you have 2 points, A and B, in FQ to the n, and you have a line through A in direction B. And you restrict the polynomial to this line, and you get a new polynomial, ht, where t is the shift on the line. And now you look at to get the derivative of this polynomial, you need to look at the gradient of the big polynomial. So this is a vector of partial derivatives with respect to all the variables. Odette? Sorry, this seems to be some activity. Is there a question?
I'm just saying that the n should be k, that's all. There's an n there.
Oh, yeah, this n should be k. Yes, thank you. In FQ to the k. And the chain rule basically said that if you have the value of the gradient at the point, and you take the inner product of this with the direction of the line, you get the derivative of the restriction. So the derivative of h at the point t is just the value of the gradient at the corresponding point of the big polynomial, inner product with the direction of the line. So if I'm a user and the server sends me all the partial derivatives at a point, I can, knowing the direction of the line, I can actually compute the derivative of the restriction. And notice that this doesn't require me to send any more information to the server. So the server knows the point a plus tb, and instead of just sending me the value, the server can just send me all the values of all the partial derivatives, and I, knowing the direction, gives me the power to get the derivative of the restriction. So, and you can do this with second-order derivatives and so on. Right. So again, this is just a single. It requires the server to just send me something that depends on a single point. So that's a good thing, and this is how the old protocols work. But now we're going to kind of try and use this idea for these exponential lines, and we'll see that there's a very annoying difficulty that comes up from the fact that we're working in mode 6 and not over a field. So to see that, I want to do something a bit annoying. I want to redefine derivatives in a way that makes the calculation, again, look much nicer. So I'm going to define a derivative of x to the L to be L times x to the L instead of L times x to the L minus 1. So it's just a different derivative. It's some linear operator. And again, the second derivative is L squared x to the L. So think of it as a derivative without shifting monomials. It's just it's a more stationary derivative. So if I have a polynomial of like g, the first derivative is given here. The second derivative is given here. Basically, it fixes the monomial and just changes the coefficients. And we do the same for partial derivatives if we have more than one variable. So for example, the second derivative with respect to x1, x2 here is just have ab times x1 to the a, x2 to the b. So the derivative of a monomial is just a multiple of that monomial. And yeah, I'm not going to use any fancy properties of derivatives later. I'm just going to use the fact that it's a linear operator on polynomials. I'm not going to use any products or any formulas for derivatives. Okay, so here we go. So again, if I have a monomial x to the u, which is x1 to the u1, so on, and I know that the partial derivative with respect to xi is ui x to the u, and then the gradient has a very nice compact formulation as u x to the u. Because u is a vector, x to the u is just a monomial, so it's just a way of writing it in a compact vector notation, which will be useful. Okay. So now, if I take the inner product of this gradient with another vector v, what I get is exactly the inner product of uv times x to the u. So that's what I'm going to need for later. All right. So now the problem is, this looks like we should be able to get our derivatives to work, but the thing that's going to cause us a problem in the next when we actually plug this into the 6 service scheme is that these inner products are in the field. They're not mod 6. So we took the vectors from the exponents where they were running mod 6, and we moved them to the field where they are they're mod 7 or mod q. That's going to be the problem, and there's a way to solve it, but just to do things a bit slower, let's pretend for the next couple of slides that we have a field of characteristic 6. Let's just pretend we have a field of characteristic 6, so everything in the exponent is mod 6, and everything in the field is also mod 6. And we'll see it's not very hard to make that happen. So, okay, so now let's see how this derivatives are going to, how we're going to use derivatives with the 6 service scheme. So we have, this is the polynomial defined by the database, and this is its gradient. So using the vector notation, it's just a sum over, over the same set of monomials with the database entries, and now each monomial is multiplied by a vector ui, which is a vector in z6 to the k. This is a vector of polynomials, but it's a gradient, so it's each entry is a partial derivative. And now what we do is we look at the same restriction, restrict to gamma to the z plus svt, where vt is again chosen to be the direction, that the secret direction in which we want to decode. Okay, so we plug that in, and this is the restriction that we had before. Now we're going to again, we observe that this is a we break apart the parts according to the inner product with in the exponents, and we get the polynomial, the final polynomial g of big S, which is this degree 5 polynomial. And recall, we're interested in the free coefficient, and big S is gamma to the little s. So far so good. Now we're going to try and get the derivative of g by taking the inner product of the gradient at a point, this exponential point, inner product with the direction of the line. So plugging this into this formula here, we just get the sum ai, inner products, vtui. And then we do the same calculation. We break everything, the sum, according to the inner products. So the inner products are just the powers of R, the powers of gamma to the S. But now they appear as the exponent, but they also appear as coefficients. So they behave very nicely. And again, we're pretending this is mod 6. So the separation is exactly as it was before. So the coefficient of gamma to the S, or big S to the R, is going to have this factor R that we can take outside. And basically what you get is just a derivative of G. So again, we're running a little slow, so maybe if this wasn't 100% clear, you can just believe me that if this was really mod 6, if the field was really mod 6, then this would give the derivative. And again, you could do a similar thing for the second derivative. So this would have worked, but now we're in the problem that this is not mod 6, this is mod 7, or mod Q. And one thing, any questions before we fix that?
So the reason of working in a field is because polynomial interpolation only works in a field, like you can't use a ring.
Well, the reason we work in a field is because this is how the previous scheme works. And you'll see in a second we'll forget about a field and we work over a ring. Any S in the exponent in the last line. There should be an S. Yes, this should be, sorry, yes, there's a typo here. In the last line, these gammas here are gamma to the S. So this is a polynomial in big S. Yeah. Thank you. Any other questions? Okay, so yes, as Anindya said, there's really no reason to work over a field. But let's just think about it for a minute. So one thing we could try to do is maybe have a matching vector family over ZQ with Q a prime or a prime power. But that this is provably impossible. As I said before, this will it will send us back to polynomial communication. Now maybe we can replace the field with the ring Z6. So this would make the field the everything work in characteristic 6, but then we have a problem that Z6 doesn't have an element of order 6, which is something that we used. So the idea is to construct a ring that has both characteristic 6 and contains an element of order 6. And it's not very hard to do. So let's see such a ring. This is an example. So take the ring of polynomials in a formal variable gamma with coefficients in Z6, and then mod it out by the equation gamma to the 6 equals 1. So so basically it's a ring of every element in this ring has the following form. It's a polynomial of degree 5 in gamma, where every coefficient is in Z6. So there are 6 to the 6 elements in the ring. And addition is pointwise, and multiplication is like multiplication of polynomials when you reduce the high powers of gamma by using the equation gamma to the 6 is equal to 1. So this has characteristic 6, and obviously it has an element gamma of order 6, just by construction. And this is a specific example of something more general called a group ring, which maybe I'll skip this for the sake of time, but it's basically you can take any ring A and any group G and combine them together to get a new ring. It's called the group ring. So this is the group ring corresponding to the ring Z6 and the cyclic group of order 6. So, and these are pretty cool things to use if you need them. Okay, so basically, replacing the field FQ with this ring, all the calculations we did before work. And I'm not going to go over them again, but just trust me that they work. But there's one part that we need to go back and look at, and that's the very last part of the protocol, where the user recovers the polynomial from the values and the derivatives that he gets from the servers. So over a field, it's trivial. I mean, if you have a polynomial, you have 2 points with second-order derivatives, you're done. But now we're working over a ring. This might not be the case, because in a ring, van der Monde matrices might have they might have determinant 0. So we have to look specifically at the matrices that come up, and so let's do this now. So here's, and this will also explain why we can't go down to one server, which we know is impossible. So, okay, so here's a general degree 5 polynomial, and now each coefficient is in the ring R. And remember, the free coefficient C0 is a multiple of AT. And because we know that AT is either 1 or 0, and because this is a power of gamma, so it's a field element, it's a ring element, but it's not a 0 divisor. So basically, the free coefficient is 0 if and only if the database bit is 0. So there's no if we can find this coefficient, we're done. We can figure out the database bit. And the question is, if we can figure this out, find this coefficient given the following 6 equations. So let's say we get the first server gives us the value, the derivative, and the second derivative at one point, and the second server gives us these 3 values in another point. And okay, so we have 6 equations over a ring. And so let's write this as a matrix. Now let's reduce it mod 6. And okay, so let's compute the determinant of this matrix. Call it M. So the determinant of M is a non-zero element in the ring. It's just it's a calculation. You can do it in MATLAB. And now there's a nice property of rings you can use that for any matrix M, there's always another matrix called the adjugate or classical adjoint matrix, such that if you multiply them, you get the determinant of M times the identity. So this is the closest you can get to inverting a matrix when over a ring. So even if the determinant is a zero divisor, you can still do this. And basically multiplying, so we have these 6 values on the left, multiplying them by the adjoint, the adjugate, gives us the determinant times the coefficients. And then we can figure out if the coefficient C0 is 0 or not, because the determinant, because C0, if C0 is non-zero, then it's not a zero divisor. So it's a pretty simple thing. Now, what happens if you try to do one server with derivatives up to order 6? Well, the determinant is just 0. And you can prove it's 0, I mean, no matter if m is 6 or any other number. So it's basically, it's pretty clear why it gets stuck at 2 servers. Just as these determinants have a formula, and the formula has factorials that you can always show these factorials will be divisible by the characteristic. So that's where it fails, and which is good, because if it worked for one server, there would obviously be a problem. Okay, so any questions?
To get because you're dealing with a ring, in general, this kind of interpolation won't work. But because you're dealing with a special set of points, or rather, not a special set of points, but you're taking 3 derivatives, 0th, 1st, and 2nd order for 2 points, it's working. But if I just give you arbitrary 6 points, this polynomial interpolation might not work.
The thing is, when you have high-order derivatives, the determinants become 0. So it's you can try, for example, to get to take matching vector families with larger. Instead of 6, for example, you take a product of 3 primes. So you can have a smaller, you can have an even bigger matching vector family. And then you can try to use high-order derivatives. But so you can show that this doesn't. Basically, the high-order derivatives add these factorials to the determinant that makes it, they basically become bigger than m very quickly. So, yeah. Okay. So here's the final 2-server scheme. So now we replace the field with a ring. We take the polynomial. We look at the same set of evaluations. The user picks a random point, a random line in direction vt. Ask each server for the values, the value at the point, all the first-order derivatives at the point, and all the second-order derivatives at the point. So the user sends k bits, or O of k bits, and gets back something polynomial in k. And once this is sent, the user can recover the value of t. So, so the final protocol is very similar. So it's basically a combination of the 3-server scheme of Fermenko with Woodruff-Yaconing derivatives trick. Now, there's some variations that we study in the paper, and then so this is just kind of the simplest example for the talk. But actually, in the paper, we only use first-order derivatives, not second-order, and this is because matching vector families, you can always assume that they have this extra structure where the inner products are, when they're non-zero, they're not arbitrary, they're always in a special set. And for that set, the first-order derivatives are enough. So it's basically you just get the 4x4 matrix. Every server sends you get again the Maxis form. There's a question, determinant 0 and so on. Yes, so there's a question. If you try to do one server and derivatives of order 5, then the determinant is 0. Was that the question? Okay, good. So that was a clarification. Any other questions? Okay, so actually in the paper we use the polynomial is degree 5, but you can show that it actually only has 4 non-zero coefficients, so it's enough to have 4 equations, and these come from values and just the first order derivatives. So that's one thing. Another thing you can do is you can encode more than 1 bit in each coefficient, so you can basically pack in more information in each database entry. That's not very difficult. A more interesting variation is you can actually replace the ring R that we worked so hard to construct with the field of 3 elements. And this sounds a bit bizarre, but the reason it works is that there's a natural homomorphism from R to F3, which basically you take gamma to -1. Again, this is why I usually use the board. But if you send gamma to -1 has order 2, and gamma has order 6. So it's a homomorphism because -1 to the 6 is still 1. But then you can also take the actual coefficients, mod 6, and send them mod 3, which is also a homomorphism. So it's a homomorphism, so it respects addition and multiplication. So all the calculations still work. And the nice thing is that the determinant that we looked at the end is still non-zero mod 3. When you apply the homomorphism to the determinant, it's still non-zero. So you can actually just invert the matrix. And somehow, this is what makes the scheme bilinear. So because before that, it wasn't really linear. It wasn't over a field. So eventually, you can get a very simple scheme. It's simple to implement because it's just over a field of size 3, and gamma is -1. So it's okay. And in general, we can reduce, so the Fermenko paper has schemes for any R. You have a 2 to the R server scheme. So we can reduce it to 2 to the R -1 servers. So the proof that the determinant is non-zero becomes more complicated in this case because it's not a fixed. We can't just compute it. We have to say something about it. And so this. So you can reduce the 4 server scheme to 2, the 8 server scheme to 4, and so on. Of course, the dramatic improvement is only when you go from 4 to 2, not. Okay, so now I was going to say something about the connection between peer and locally decodable codes, but I'm running out of time, and I want to talk about some open problems. So you can look at the slides later. So we have this kind of new result on 2 server schemes, and the question is if you can push it even further and get even better communication. So as I said before, taking more derivatives sounds like it might help. So the general construction of Grolmush for matching vector families says that if you have if M is a composite number with R prime factors, then you can have a matching vector family of size exponentially in log to the RK. Or so if you could somehow use if you use this scheme for peer, you get communication which is exponentially in log to the 1/R. So we used it for R equals 2. But you can hope to use it for maybe any constant R. That would be very nice. So again, our technique doesn't work here because the determinants vanish. So maybe there's a more clever way of doing it that we didn't see, but the direct way, asking for 2 servers and asking for derivatives of order m/2, just doesn't cut it. And so this is one direction, using bigger matching vector families for bigger composites. Another direction, which is again obvious, is okay, maybe you can just construct larger matching vector families, and that's a great question. There are no lower bounds. There's like a logarithmic lower bound of sorry, let me just say it again. So in terms of upper bounds, so in this case, upper bounds are limitations. Upper bounds say that you cannot construct matching vector families that are too large. The best upper bound is in a joint work with Baumik and Lovett, and where we show the upper bound, which is exponential in k over log k. So exponential in k is trivial, but exponential in k over log k is we had to work for that, and that's conditional on some conjecture called the polynomial Farman-Rorschach conjecture in Zm. So if this was tight, this would give two-server peer scheme with log n communication, which would be very nice. So, but I don't think it's tight. It's probably not tight. Okay, so that's all I had to say. Thank you.
Thanks, Ed.
I'm imagining clapping now. Okay. Okay.
I've got a very small question regarding the very last thing you said.
Yeah.
You have, basically, you've got something that, you've got a matching vector family provided a conjecture. I guess it's not a constructive proof. I mean,
the matching vector family, you mean the construction of Grolmusch?
Like, what exactly is the result, assuming the conjecture? What exactly is the result?
The result, you mean what I mentioned here with Baumik and Lovett, or?
Yeah, the current upper bound, which is n at.
Oh, okay. Yeah, so this is an upper bound. It's a proof that you cannot have a matching vector family of size bigger than x k over log k. So in terms of upper bound here means a limitation. It's a limitation result. So it's not a construction.
Okay. Yeah,
it flips the direction. The bigger the family is, the better, the smaller the communication.
Thanks.
Okay.
Question?
Yes. Hi.
Hi. So you said that if you take M that has more than 2 prime factors, then just determinant has, this matrix is 0 determinant. But you could try and get more derivatives than M over 2, like some constant, and try to see together the information that you need.
So again, you're saying you can ask for derivatives of order bigger than M over 2, or?
Ask for derivatives up to order 100M. And then you can see whether this gives you enough information to recover the coefficient that you need.
Yeah, you can try to get some linear combination. It doesn't even have to be derivatives. I mean, you can try to get some linear combinations and solve some system. It's not you're not limited to any specific thing. We just couldn't find any way of doing it. I don't know if that was the question.
Okay.
Just start talking.
Yeah. Hi. First of all, Zeev, beautiful result. Congratulations.
Thank you.
A small question about the privacy. You talked about one-directional privacy, in which the two servers do not learn anything about the index T. On the other hand, the verifier received more information than what he asked for.
Right.
He receives a T, but he gets additional coefficients. Is there a way how to modify your scheme in a way that the servers might change the data structure, add random elements to them in such a way that the verifier will learn only AT and nothing else? I can see how to do it if the two servers were allowed to communicate with each other at the preliminary phase before the database is given to them. So you would agree on some common randomness.
So it's a studied problem. I can't remember the actual paper, the name of the authors off the top of my head, but so I think what you said is right. If they actually, I think the model needs to be that they share, they have shared randomness, And I think you can show that they have to have some kind of shared randomness for that to work. And I think there's a general reduction that adds one more server. So you go from 2 to 3 server, and you get, it's called symmetric peer.
No, but in our scheme, I am pretty sure that you can add a small number of random values. Think about all the AIs. The other coefficients that not the zero coefficient are likely to be some kind of function that you can analyze over the whole database. So if the database will contain sufficiently many random bits which were added, then all the other coefficients are going to be random as far as the verifier is concerned. So the question is, what's the minimum number of bits have to be added?
Right. So this is we didn't think about it too much, but it's a well-known model where there's shared randomness and you're trying to have symmetric privacy. So it's a good question. I mean, I haven't thought about it too much because I think at least the model itself is not as natural. I think because you need to share a lot of randomness between the servers, and it's not clear how realistic it is.
In your scheme, I'm pretty sure you don't have to share a lot of randomness, just a few entries.
So yeah, if it's a few entries, that would be interesting. But I'm guessing it's more than a few, but not sure. Okay. Any other questions?
Okay. Thank you, Zeev.
Yes.
So I guess we can go ahead now.
Maybe you want to mention the next talk for those who are still here.
Okay, yeah, so the next talk is by Harry Berman in 2 weeks' time, and that's on catalytic computation, so it's a very exciting topic. And 2 weeks after that, there's Alan Sly, who's going to talk about case and threshold.
Okay. Thanks again, everyone, for joining, and those in Europe, good night. Also, thanks to all those who joined us through the YouTube. We had about 10 viewers there. Okay, so see you next time, everyone. I'm going offline.